I'm going to go through this example problem where we determine the fugacity of a vapor mixture using an equation of state. The problem statement says, consider a ternary system of methane, ethane, and propane at 25 degrees Celsius and 15 bar. Assume the system can be represented by the virial equation truncated at the second term. So it gives us an equation of state, and it gives us an expression for the Bmix. And at 25 degrees Celsius, the second virial coefficients are given by the following constants in centimeter cubed per mole. Part A asks us to develop an expression for the fugacity coefficient of methane in the mixture. To do this, I'm going to use equation 7.14 in the textbook, which relates the vapor fugacity in a mixture to the change in pressure of an equation of state. This is equation 7.14 when it's applied to methane in our ternary mixture. What we need to do to proceed with the problem is to find an expression for partial P over partial NA. From this given equation of state, we can turn it into a pressure explicit equation by substituting in PVm over RT for the compressibility factor Z. From here, we can substitute in that Vm is equal to V over N and rearrange the equation. To get this equation as a function of Na, I'm going to substitute in that N, the total number of moles, is equal to Na plus Nb plus Nc, and that Ya, Yb, and Yc is just going to be the ratio of the moles of A, B, and C to the total moles. When you substitute these in and simplify, you'll get this expression for the pressure. Now take the partial derivative with respect to Na. I'm going to denote this expression here, 2NA plus 2NB plus 2NC as the constant theta to save some writing. I'm going to plug this derivative into the integral on the right side of equation 7.14 and evaluate the integral. Now that the right side of equation 7.14 is solved, I'm going to equate it to the left side of equation 7.14. To simplify this even further, I'm going to cancel out the p low in the denominator of the natural log on both sides, and I'm going to let p low go to 0. To get this equation in terms of the fugacity coefficient, I'm going to subtract ln of p from both sides. You can see that this is the fugacity coefficient, and this right here is just 1 over z. Now we can take the exponential of each side. From here, to get this in terms of the mole fractions and the molar volume, we just divide by the total moles on top and bottom of the equation. This is the final answer for the fugacity coefficient in part A. Part B says that if the mixture is 20 mole percent methane, 30 mole percent ethane, and 50 mole percent propane, estimate the fugacity and the fugacity coefficient of methane for the mixture. So for this, we're going to use the equation that we found in part A, using that Ya is 0.2, Yb is 0.3, and Yc is 0.5. But we also need to solve for Z and molar volume in this expression. First, we need to calculate the value of Bmix with this equation right here. And when you calculate it, you need to remember that these constants, BBC, and all of these virial coefficients are given in centimeter cubed per mole, and we want this in meters cubed per mole. So in your conversion, make sure to account for that. And when you do the conversion, you get that Bmix is equal to negative 2.392 times 10 to the negative fourth meters cubed per mole. Now to find Vm, we're going to use the equation of state and plug it into an equation solver. So when you plug it into an equation solver, you get that Vm has two possible values. So we're going to have to check each of these to figure out which one is the most reasonable value to use. So when you try each of the two values, for the first one, you get that the fugacity coefficient is going to be 2.75, and for the second one, you get that it is 1.04. And so in the problem statement, it said that the pressure was 15 bar, which really isn't that high considering a lot of the fugacity problems that we deal with. So a fugacity coefficient of 2.75 is much more likely for a very high pressure, say over 50 bar. So we're going to assume that this fugacity coefficient of 1.04 is much more reasonable in this case. Now to get the fugacity of A in the mixture, all we're going to do is multiply the fugacity coefficient by the partial pressure of A. We get as our final answer for the fugacity of A in the mixture is 3.12 bar. Now for part C. In part C, we're going to repeat parts A and B, except we're going to use the Lewis Fugacity Rule. So the Lewis Fugacity Rule assumes that the fugacity coefficient of a species in a mixture is equal to the fugacity coefficient of the pure species itself. So in this case, we're not going to treat it as a mixture, we're going to treat it as pure A, so the total moles is going to be equal to just the moles of A as well. With that, Bmix is now going to be equal to just Ya squared Baa. I'm going to start again with equation 7.14, except this time the fugacity of A is going to be just the pure fugacity of A in the expression. Just like in part A, we're going to use the equation of state to get an explicit expression for the pressure. Take the partial derivative of this with respect to Na. Again, to save some writing, I'm going to now denote this expression right here as a constant theta. So at this point, we have the same thing as we did in part A, where the partial derivative of pressure with respect to Na is RT times 1 over V plus theta over V squared. And we're going to go through the exact same steps as we did in part A, and we'll actually obtain the same expression for the fugacity coefficient. So I'm not going to write everything out, but we're going to do the same steps as we did in part A with this expression right here, and we'll get the following for the fugacity coefficient. Here, the only thing different from what we had in part A is that our theta is a different constant. Again, to get this in terms of mole fraction and molar volume, we can divide through by the total moles on top and bottom. So this is our final answer for the fugacity coefficient in part C. Now to get the numerical value of the fugacity coefficient, we need to solve for the molar volume. You can use an equation solver to solve for the molar volume, and again, you'll get that there are two possible options. The first one is 4.31 times 10 to the negative 5th meters cubed per mole, and the second is 1.61 times 10 to the negative 3rd meters cubed per mole. In part A, when we had two options for the molar volume and we had to figure out which one was more reasonable, we ended up choosing the bigger value for the molar volume. So in this case, we are going to choose the larger volume of 1.61 times 10 to the negative 3rd meters cubed per mole. Using this chosen value, we can solve for V and plug everything into the expression up here for the fugacity coefficient and solve for it numerically. When you plug everything in, you'll get the final answer that the fugacity coefficient of A in the mixture is 0.975. So in calculating the fugacity of A in the mixture, it's important to note that the value of Ya right here is going to be 0.2 and not 1 like we were using for the calculations of the fugacity coefficient. That's because the Lewis Fugacity Rule only affects the calculations for the fugacity coefficient, and you can only equate the fugacity coefficient of a mixture to the pure species and not the normal fugacity. So in this case, the value of Ya is going to be back to its normal fraction in the mixture of 0.2. So the final answer is that the fugacity of A in the mixture is 2.93 bar. I hope you learned something from this video and that it helped you understand how to solve the problem. If you like this video, give it a thumbs up and subscribe, and we'll be posting weekly videos for homework help in Chemie 211 at Purdue University.